Hello and welcome to problem set number 8. Our topic today is molar mass, mole ratios, and stoichiometry. If you have not already done so, I do make all of the worksheets for these problem sets available online through my website. It will really be helpful to you to have that in front of you as you go along and solve these problems. All right, so let's start with number 1. Calculate the molar mass for the following substances. We have an A, B, and a C. A is water. And notice that I didn't give you the formula. This is going to give you a little bit of practice with writing formulas yourself. Water is a common name, so make sure you know the formula is H2O. All right, so check your periodic table so you can calculate the molar mass. The mass for the one oxygen is 16.00 grams, and each hydrogen is 1.01. I'm just going to round everything to the 100th decimal place. So 1.01 2 times. Okay, so I'm going to go ahead and do it twice like this. So we get 18.02 grams per mole for the molar mass of water. Okay, so that's the mass of 6.022 times 10 to the 23rd water molecules. All right, B, the molar mass for calcium chloride. Calcium is a metal, chlorine is a nonmetal, so we're talking about an ionic compound. So if you want to get this formula right, you've got to check the charge. Calcium is a group 2A metal, so a 2+ charge on that cation. Chlorine is a group 7 nonmetal, so a 1- charge on the anion. So the ratio is going to be 1 calcium cation to 2 chloride anions. So CaCl2. All right, so now we see that we need to add up the molar mass for 1 calcium and 2 moles of the chloride anions. Okay, so check your periodic table. Calcium is 40.08. 1 mole of calcium is 40.08 grams, and chlorine is 35.45, but it's times 2. So let's do this way. 35.45 grams, that's times 2. Okay, we're going to add those together. All right, I'm going to use my calculator so it goes a little faster. 35.45 times that by 2, add in that 40.08, and I get 110.98 grams per mole. Okay. All right, going on to C, sodium carbonate. Another ionic compound, so make sure that you get your formula right. If you don't write your formula correctly, you're not going to calculate your molar mass correctly. Okay, so sodium is a group 1A metal. Carbonate is a polyatomic anion that you hopefully have memorized as CO3 with a 2- charge. So it's going to take 2 sodium cations for every 1 carbonate anion, which is why we're going to write the formula as Na2CO3. That's going to be a lot to add up for our molar mass. We've got 2 moles of sodium, 1 mole of carbon, and 3 moles of oxygen. Okay, so 2 times the molar mass for sodium, which is 22.99, plus the 1 mole of carbon, which is 12.01, and the 3 moles of oxygen, which are 16.00. Okay, and add all of those together. So we've got 2 times the 22.99 plus the 12.01 plus the 3 times 16. I get 105.99 grams per mole. Okay. All right, we're going to go on to number 2. So I'm going to go ahead and erase all of this right here. Okay, Number 2, how many atoms of carbon are in 1 mole of carbon dioxide? Okay, so in 1 mole of carbon dioxide, there are 6.022 times 10 to the 23 molecules of carbon dioxide. So how many individual carbon atoms? Well, each molecule has 1 carbon atom. So it might help to think of it this way. In 1 mole of CO2, there are 6.022 times 10 to the 23rd molecules of CO2. Avogadro's number for the mole. And in every 1 molecule of CO2, there's just simply 1 carbon atom. Okay. So if you want to know how many atoms of carbon, it's going to be 6.022 times 10 to the 23rd. Okay. All right, number 3. We don't have to erase, we can put it right below here. How many atoms of oxygen are in 1 mole of carbon dioxide? Okay, well, in 1 mole of carbon dioxide, we already said there are 6.022 times 10 to the 23 molecules. Remember, it would be like saying 1 dozen carbon dioxide. We'd know that there are 12 in a dozen. It's the same concept. We know that there's 6.022 times 10 to the 23 in 1 mole, okay? And in this case, in 1 molecule of CO2, there are 2 oxygen atoms. Look at the formula, 2 oxygen atoms in every molecule of CO2. So to figure out how many individual atoms of oxygen, we're going to times 2 times Avogadro's number. So I'm just going to go ahead and do it this way, 12.044 times 10 to the 23 oxygen atoms. Okay, should circle those answers. Okay. All right, number 4. How many molecules of carbon dioxide are in 1 mole of carbon dioxide? Well, we don't really even need to do the calculation. I think you're getting the idea here. In 1 mole of a substance, there is Avogadro's number of objects. So in 1 mole of carbon dioxide, there's 6.022 times 10 to the 23 CO2 molecules. Okay, that's what mole stands for. All right, let's go ahead and erase this before we go on to number 5, because number 5 has A and a B, and I think it's going to take up a little bit of room. Okay, so number 5. A typical cup of coffee contains around 95 milligrams of caffeine, and you're given the molecular formula for caffeine as C8H10N4O2. Yikes, it's kind of a scary looking molecular formula. Answer the following questions about caffeine. So A, how many moles of caffeine are in a typical cup of coffee? Okay, so we know how many milligrams, okay, and we know that we can convert between grams and moles using a molar mass. Okay, so to convert between grams of a substance like caffeine and moles of the same substance, we would use a conversion factor that we called in tutorial 8 the molar mass. We would need to calculate the molar mass of this molecular formula for caffeine. Okay. But unfortunately, we've got milligrams here, not grams. So we have to go all the way back to tutorial 1, where we learned about the metric system, and first figure out how many grams is in 95 milligrams. So I'm going to write here, the metric system. Coming back to haunt you, okay? And it's going to do that throughout your entire chemistry career. You're going to have to remember the metric system. All right, so let's do this problem. So I'm just going to write an overview of what we're doing. We're taking 95 milligrams of C8H10N4O2, and we're trying to figure out how many moles of C8H10N4O2 of caffeine. Okay, so that's what we're trying to figure out. And we already said we're going to do it in these 2 steps. So take your 95 milligrams of caffeine. And I know it is tedious to write this over and over and over again because it's a long molecular formula, but it is good note keeping, and I do recommend you do it, okay? And in every 1 gram, there are 1,000 milligrams. All right, so we just converted into grams of caffeine by dividing by 1,000. And we're going to do our second step. Now that we have it in grams, we're going to turn it into moles by using its molar mass. So grams will go on the bottom. So that they'll cancel out. And the mole, remember that molar mass is always the number of grams in 1 mole, so it's always going to be 1 up here. 1 mole of C8H10N4O2. Okay, so what number do we put here? It's going to take a little while. Grab your periodic table and get adding. All right, we've got 8 carbons at 12.01 grams per mole each. We've got 10 hydrogens at 1.01 gram per mole each. We've got 4 nitrogens at 14.01 grams per mole each. And we've got 2 oxygen at 16.00 grams per mole each. Okay, remember where I get those? I get those from the periodic table. You should not have those memorized. Eventually you'll start memorizing them if you use them enough, but please take the time and look at your periodic table and make sure you know where I got this number for the molar mass for carbon, and I multiplied it by 8 because there's 8 of them in this molecular formula. Where I got the molar mass for hydrogen, why I times it by 10 because there's 10 of them in this formula. Where I got the molar mass of nitrogen, and why I multiplied it by 4, there's 4 of them in this molecular formula. And where I got this molar mass for oxygen. It's all from the periodic table, not from your memory, okay? All right, now let's add it up so we can figure out what number to write here. So 8 times 12.01, and I'm going to add in the mass for the hydrogen, and then I'm going to add in the mass for the nitrogen, and last but not least, my 32 for the oxygen. 194.22 grams per mole. Okay, so 194.22 goes right here. Okay, I'm going to erase this work here just so that it doesn't get too messy up here. Okay, so now I'm ready to punch in the whole problem. 95 divided by 1,000 divided by the 194.22 grams for the molar mass of the caffeine. Okay, so 95 and divided by the 194.22. Okay, put my answer down here. I get 4.9 times 10 to the negative 4 moles of caffeine. Okay, I'm going to circle that. and I rounded to the 2 digits for the 2 digits I started with. Okay, my calculator gave me a lot more digits than that. Okay, all right, let's go on to part B of this problem. Let's see if we can squeak it in here. I think we can. So B, all the way down here. How many molecules of caffeine are in a typical cup of coffee then? Okay, well, if this had come out to be 1 mole, then it'd be easy. It'd be Avogadro's number. It'd be 6.022 times 10 to the 23rd molecules. But it didn't come out to be 1. It came out to be 4.9 times 10 to the negative 4. So let's take 4.9 times 10 to the negative 4 moles of caffeine. And in every 1 mole, I know how many molecules there would be. There would be Avogadro's number, 6.022 times 10 to the 23rd molecules. Okay, so think about what you're doing here. It's kind of like saying a dozen is 12. So what if I only have a half a dozen? Okay, what if I only have half a dozen, then I would take 0.5 times 12 and I would get 6, right? You probably don't really have to write that out to do it. You could probably do it in your head. But that's really all we're doing here. We don't have a whole mole, so we can't just say 6.022 times 10 to the 23rd. We have a fraction of a mole, so we have to multiply that through just like we would multiply half times 12 to figure out half a dozen. Okay. All right, so the 4.9 to the negative 4 times 6.022 to the 23rd. Okay. We get 2.95. So I'm going to go ahead and round that up. I'll go ahead and write the whole number first. Times 10 to the 20th. I'm going to round that here, so it's going to be 3.0 times 10 to the 20th molecules. And I'll go ahead and write molecules of C8H10N4O2 so that we know that it's molecules of caffeine, not molecules of, nitrogen dioxide or something different. Okay, it's always good to have good note keeping. All right, we will definitely not have room for number 6 here, so let's erase before we go on. Okay, so number 6 is our last problem, but it has an A through G and it's all stoichiometry, so some good practice here. Cisplatin is a chemotherapy drug used to treat a variety of different types of cancer. It is synthesized from potassium tetrachloroplatinate and ammonia through the following reaction. So A asks let's put it down here. What is the mole ratio between the 2 reactants? So I'm going to go ahead and write the reaction up here. It's already in the worksheet for you, so hopefully you have that printed out in front of you and you don't have to take the time to rewrite this. Okay. All right, so what is the mole ratio between the 2 reactants? So we can see it's a 1-to-2 relationship. So 1 mole of the potassium tetrachloroplatinate to 2 moles of the ammonia. And if you wrote in reverse, that's okay too. Just make sure the 2 is with the ammonia and the 1 is with that potassium compound. All right, B, what is the mole ratio between potassium tetrachloroplatinate and cisplatin? Okay, that would be this product right here. So we can see that it's a 1-to-1 relationship for B. For every 1 mole of that reactant, we get 1 mole of the cisplatin. Okay. All right, C. How many moles of cisplatin can form from 2.50 moles of the potassium tetrachloroplatinate. Okay, so the question is, how many moles of the product cisplatin? Okay, and I think I've mentioned this before in previous problem sets, that I like to do a little flow chart of what I'm trying to solve, so a little summary of the problem here. I always pull that out of a word problem. It helps me somehow to keep track of things, because these problems can get very, very long. This is not a very long problem. All we have to do here is find the mole ratio, which we already found on B, and set it up so that we convert from moles of the potassium tetrachloroplatinate into the moles of the cisplatin. Okay, so my 2.50 moles of the potassium tetrachloroplatinate, for every 1 mole of the potassium tetrachloroplatinate, I'm going to make 1 mole of the cisplatin. Okay, so you're just timesing by 1, dividing by 1, so your answer does not change. You're going to make 2.50 moles of the cisplatin. Okay. All right, going on to D. I think we can squeak one more in here. D. How many grams of cisplatin can form from 8.13 moles of the potassium tetrachloroplatinate? Okay. So again, I like to start off with a little flow chart. So from 8.13 moles of the potassium tetrachloroplatinate, how many grams of cisplatin can I get? Okay. All right, so this is not a one-step problem. A one-step problem will be going from the moles of the potassium tetrachloroplatinate into moles of the cisplatin. We need to do an additional step after that and convert the moles of the cisplatin all the way into grams of cisplatin. So if you have your flow chart from the tutorial, slide 4, the flow chart at the end, get it out. It's very helpful here. Okay, so I'm just going to do an overview of what we're going to do. We're going to take our moles of the potassium tetrachloroplatinate. We're going to figure out the number of moles. So this is just kind of an overview. I'm just kind of brainstorming right now. We're going to figure out the moles of the cisplatin. How are we going to do that? We're going to do that with the mole ratio. Let me write that in a different color. Mole ratio. Okay, which is 1 to 1. We just saw in the previous problem. And once we know how many moles of cisplatin, we can now use the molar mass of cisplatin to figure out the number of grams. Okay, so let me write in blue. For this, we're going to need the molar mass. I'm just going to write NM for molar mass. Well, where do we get that? From the periodic table. So we have our work cut out for us here. Okay. All right, so really, we already did this first step up there, but I'll go ahead and set it up and pretend like we didn't do it already, because it's good practice. Okay, whoops, and it's not 2.50 moles, sorry. It's 8.13 moles of that potassium tetrachloroplatinate. Okay, and for every 1 mole that reacts, you're going to get 1 mole of that product. How do you know? Because I gave you the balanced chemical equation up here, and it's a 1-to-1 relationship. Okay, so we've already figured out how many moles of cisplatin are going to form, and for every 1 mole of the cisplatin, we can figure out how many grams by calculating the molar mass. So the number that goes here will come from the molar mass. Let's do the molar mass off to the side over here. Okay, so well, let's do it over here because my periodic table is over here. All right, so let's look up the molar mass for the platinum. 195.08. Okay, that's for my platinum. Now there is not just one nitrogen, there's two. So I'm going to do 2 times 14.01 for the mass of my nitrogen. Notice there's 3 times 2, there's 6 hydrogens, so 6 times 1.01. And then there's 2 chlorines, so 2 times 35.45. Whew, it's a lot to add up. Okay, gonna need a calculator here. 195.08. Adding in my 28.02 for my nitrogen, adding in my 6.06 for my hydrogen, and my 2 times my 35.45. My goodness, we get 300.06 grams per mole. Okay, so that's the number that goes here, 300.06. Moles of cisplatin cancels out. We're left in grams of cisplatin. What were we seeking up here? We were seeking grams of cisplatin, so it's a good indication we've done everything right. So now take your 8.13 and times that 300.06. You get 2,439.4878 grams. And I'm going to go ahead and round that off. So I'm going to need to use scientific notation here. So 2.44, so I'm going to round up because this is a 9, times 10 to the 123 grams of PTNH3 2Cl2 cisplatin. Ooh, that's ugly. But there it is. There's our answer. Okay. All right, so let's definitely erase because I cannot write anything more on this board. We will leave the equation up. Okay. How many moles of cisplatin can form from 1.33 moles of ammonia? Okay, so remember I like to do my little flow chart. I'm trying to figure out how many moles. Is that right? How many moles? Yes. How many moles of cisplatin can form, okay, from this quantity of ammonia? So we're going moles to moles. So all I need here is my mole ratio. It is not 1 to 1. It is 2 to 1. So let's set this up. 1.33 moles of ammonia. For every 2 moles of ammonia, you make 1 mole of the cisplatin. All right, so 1.33 divided by 2, and we're done. We get 0.665 moles of the cisplatin. All right, so I think we can fit in F and hopefully also G. How many grams of cisplatin can form from 12.19 moles of ammonia? So 12.19 moles of ammonia. How many grams, not moles, but grams of cisplatin do we get? Okay. All right, so this is not going to be a one-step problem. It's not just going through the mole ratio. It's going through the mole ratio to figure out how many moles of cisplatin, followed by using the molar mass to convert moles of cisplatin into grams of cisplatin. So if you have that flow chart, again, from the tutorial notes, slide 4, that's very helpful to kind of see, to use that, to see what your steps are going to be in this kind of problem, okay? So let's take the 12.19 moles of ammonia, and let's use our mole ratio, just like we did up here, to figure out how many moles of cisplatin are going to form. Okay, and that doesn't finish it off. We want to go all the way to grams, so we need the molar mass of the cisplatin, which, oh boy, I don't think I still have it. No, I don't still have it. We're going to have to do it again. 1 mole has a certain number of grams. I think it was 300.06, but my memory fails me a lot. So, good practice. We'll just add it up again real quick. If you didn't get it the first time, maybe you'll get it this time, okay? So we're adding up the molar mass again of cisplatin. So platinum was 195.08. The nitrogen is 2 times the 14.01. The hydrogen is going to be 3 times 2, so it's going to be 6 times the 1.01. And then 2 times the 35.45 for the 2 chlorines. Add it all up. 195.08 plus the 28.02 plus the 6.06 plus the 300.06 grams per mole. Okay, we did that already, but we had to do it again because I erased it. All right, 300.06 grams for every mole of cisplatin. That's its molar mass. And we got all these numbers from the periodic table. For 1 mole of platinum, 2 moles of nitrogen, 6 moles of hydrogen, and 2 moles of chlorine. All right, we're ready to figure out the answer. So 12.19. We're going to divide that by 2. We're going to times by the 300.06. Okay, we get, I'm going to write the whole number first, 1,828.8657. I'm going to go ahead and cut that off for the 4 digits here. Make it 1,829 grams of cisplatin. And I'll circle my final answer there. Okay? All right. Last but not least, G. And I'm going to erase the molar mass calculation here so we have a good amount of room to do our final problem. How many grams of cisplatin can form from 25.00 grams of potassium tetrachloroplatinate? So again, I like to start with just a simple overview of what I'm trying to do here. So 25.00 grams of the potassium tetrachloroplatinate, and I'm trying to figure out how many grams of the cisplatin can form. Okay, so if you have that flow chart from the tutorial notes on slide 4, get it out, look at it. Look at what we're trying to do here. We're trying to convert between grams of one substance and grams of a completely different substance in this balanced chemical equation. The only way that you can quantitatively relate two substances is through their mole ratio. So we are definitely going to have to convert moles of the potassium tetrachloroplatinate into the moles of the cisplatin. That's the only way that we can quantitatively relate those two different substances. Okay, so a mole ratio is going to be needed. So I'll write here mole ratio. Okay, but we don't know how many moles of the potassium tetrachloroplatinate. We only know the grams. So we're going to need to be able to convert the grams which is the 25.00. We're going to need to be able to convert that into moles. We convert between grams of a substance and moles of the same substance by using the conversion factor called molar mass. I'm going to just write MM. And we get a molar mass from our balanced chemical equation. Or excuse me, from our periodic table. We get the molar mass from our periodic table. All right, we're not asked to express our final answer in moles of cisplatin. We're asked to express our final answer in grams of cisplatin. So we're also going to need the molar mass of cisplatin. Good thing I didn't erase it again, so that we can convert and figure out the number of grams. We don't want to leave it in moles. Okay, so we're going to need the molar mass of cisplatin as well. Okay, so that's a little flow chart. It'll match up with the flow chart from the tutorial notes. A little flow chart of what we're going to do. Okay, let's do it. 25.00 grams of the potassium tetrachloroplatinate. We want to turn that into moles, so I'm going to put the grams on the bottom and the mole on the top. Okay. And we need to figure out the molar mass so we can plug it in there. Okay. This one we have not calculated yet, so let's go ahead and grab our periodic table. I'll move it over here so that I can do that. Potassium is 39.10. There's two of them, so it's going to be 2 times the 39.10 for the molar mass of the two potassiums, 2 moles of potassium. The platinum was the 195.08. And the chlorine are each going to be 35.45, but there are 4 of them, so 4 times 35.45. All right, add all that up. 2 times the 39.10. Add in the 195.08. And add in your 4 times 35.45. Okay. 415.08. Right, that's the molar mass of the potassium tetrachloroplatinate. Okay. All right, so let's write that in here. 415.08. So now my grams cancel out, and now if I do this calculation, I will know how many moles of the potassium tetrachloroplatinate are reacting. Okay. All right. Now I'm ready, so I just did this step. Now I'm ready to convert my moles of the potassium tetrachloroplatinate into my moles of cisplatin using my mole ratio, which is 1:1 from the balanced equation. For every 1 mole of the potassium tetrachloroplatinate, I get 1 mole of my cisplatin. Okay. I just did this step and converted between moles of potassium tetrachloroplatinate into moles of cisplatin. So I now know how many moles of cisplatin are going to form. Okay. I don't want to leave my answer in moles. I want it in grams. The problem asks for grams. So fortunately we still have our molar mass up here for cisplatin. So for every 1 mole of cisplatin, there are 300.06 grams of cisplatin. Ooh, it's a lot of work. All right, so let's pull out our calculator. Divide by the 415.08. Okay, times 1, divide by 1. Won't change our answer. Times 300.06. And my answer is unrounded first, 18.07, 241977. I've got 4 digits here, so I'm going to round off to 18.07 grams of cisplatin. Okay. So these kinds of problems take practice. If you need more practice, I highly recommend having that flow chart from the notes in front of you as you're going through all of your practice problems, and then eventually there will come a time when things click and you won't need that flow chart anymore, and that is when you have committed stoichiometry to memory, and that's wonderful. Okay, so this will conclude our problem set number 8. Please consider tuning in to tutorial number 9. Thank you.